Well, hello 381. So what I'd like to do in this video is get you prepared for Professor Jarbo's lecture, which is just a couple of steps ahead of where we left off today. So what we're preparing for is what we would like to be able to do next is apply second law concepts to open systems. So the basic idea is we have some process and we have a flow stream or two going in and another flow stream or two going out, and there could be some heat associated with that process as well. So for the first law energy balance for an open system, we had the following. We had delta m dot u plus delta m dot h plus m dot u squared over 2 plus m dot zg for kinetic and potential energy terms. That was all equal to the heat plus the work of the process. For the second law, entropy is not conserved, but what we're going to be doing is something similar. We are going to be doing an entropy balance. So like we had for the energy balance, the entropy balance is as follows. And this should be the time derivative, sorry, not the delta, up at the front there. So we're going to have the time derivative of the change in entropy for the control volume that defines the process. So that is going to be the boxed region right there. And for steady state processes, we're usually going to be dealing with steady state processes. So often we'll be able to cancel out that term. Okay, so the next component of an open system entropy balance then is going to be an account for the entropy contained in the flow streams that goes in and out of the process. So we are going to have a delta m dot s for the flow streams. And what we're calculating over here on the right is going to be a quantity that we call Sg dot. And what this is the rate of energy generation. All right, and so by the second law, this has to be greater than or equal to 0. All right, so now there's one more piece of the entropy balance that we need to account for, and that is this heat term right here. And so that comes into play through an additional term where we account for the heat, and remember that ds is equal to dq over t, and so that's where that is right there. So this q term is going to be whatever heat flow is associated with the process, and there could be more than one. The temperature that appears in the denominator, this is going to be the temperature of the surroundings. So if there is heat being ejected to a cold river, for example, then the T sigma would be whatever the temperature of the river is. And the sign of this Q needs to be defined such that it all makes sense. So the Q arrow that is drawn on the process here is showing the Q going out of the process. So this Q is negative with respect to the process. So the surroundings, it's accepting that heat, that entropy is going up. So we need to have the minus sign in front of there to make sure that we are getting the amount of entropy generated by that heat transfer captured. Okay, now the effect of the heat transfer on the process is going to be contained within the state change of the flow streams. So if there was heat going into the system, then the entropy of the flow streams would be increasing, and that the effect of that heat would be captured in this flow stream term. The effect on the surroundings then would be to decrease the entropy. So the Q would have a positive algebraic sign, and then the surroundings term would have a correct decreasing impact on the total amount of entropy generation. So this middle term here is what we need to focus on next. So we need to calculate the state change of the flow stream. And to be able to do that, we need to figure out how to do state change calculations for some simple materials. And the simplest material, of course, is the ideal gas. And so that's where we start for now. So where do we start with that? Well, just about everything in thermodynamics starts with the first law. And then once you start talking about entropy, then we add the second law into that. So let's do that. We start with the first law in differential form. du equals dq plus dw. All right, and now let's rearrange that for the heat. So the dq is equal to dq is equal to du minus dw. And then we're going to use the second law expression that says that heat and entropy are related to each other. So we insert that into the left-hand side as TdS. And now we can make our common substitutions for the internal energy and the work terms. So we're going to have CV dt, and then we're going to have plus P dV, as we've done before for the work term. And so the only difference now is that we have TdS on the left instead of the heat term. All right, so we can integrate that if we want to. So if we go to ideal gas mode, so we'll say IG gas state, I'm going to divide through both sides by temperature and then integrate. So the integral of ds is equal to the integral of, I'm going to pull the r out, and it's going to be CVIG over r in the integral, and then plus dt plus the pressure is going to be r. So for the ideal gas state, the pressure is RT over V, right? So that's going to be RT over V. I divided through by T, so I need a 1 over T down here. And then I'm going to be left with just dV over V. And so the integration limits for the temperature integral are going to be from T0 to T. For the volume integral, it's going to be V0 to V. And for the entropy integral, it's going to be S0 to S, and so that all evaluates to delta S equals R times my heat capacity integral, which I'm going to leave as is for the moment, plus R times the natural logarithm of the ratio of the final and initial volumes. All right, so that's all well and good. And if I wanted to, I could either treat the heat capacity as not temperature dependent and pull it out of the integral, or I could insert the polynomial correlation, and for the constant pressure heat capacity, and then subtract appropriately to turn that into a constant volume heat capacity. But at this point, I'm going to note that this equation is in terms of T and V, and often we prefer to have temperature and pressure as our primary independent variables. So let's back up a couple of steps to equation 15, where I still have du plus dw, And what I'm going to do is I'm going to make a couple of simple adjustments. So we're going to say dq is TdS like it was before. And now instead of converting du into CV dt, I'm going to first add the differential of PV to U. And what that does is it turns it into dH. U plus PV is H. And the work term, that still turns into P dV. And now, since I added the differential of PV, to leave the equation correct, I also need to subtract PdV, or the differential of PV. And so the differential of a product, we use the chain rule for that. So that's minus PdV minus V dP. So we're going to have minus PdV minus V dP. And we can see that the work term cancels off with the one generated from expanding the PV differential. And what I'm left with is TdS equals dH minus V dP, which I can then integrate now to find what the change in entropy is for a change in temperature and pressure for an ideal gas. So let's go again to the ideal gas state and divide through by T again. So this time I'm going to make use of the fact that dH is equal to the constant pressure heat capacity times the differential temperature change. So dH in the ideal gas state is Cp Ig dt, and since I'm dividing through by temperature, that is going to be accounted for right there. And then for an ideal gas, the volume is RT over P, and so we're dividing through by temperature, so I'm going to be left with R times dP over P. So there is state changes for ideal gases in differential form, and then to get to a delta S, we're going to integrate both sides. So when we do that, I'm going to have delta S, and I'm going to pull out an R and then divide by R because it's Cp over R that appears tabulated, and we can look up in the textbook. So that's going to be Cp Ig over R dt over T minus R. And now the integral of the dP over P integral is just simply going to be natural log of P over P0. Okay, so the thing that we want to focus on next is how do you evaluate that integral. It's pretty straightforward. The standard correlation that we use is just a simple polynomial fit. So again, there's no pressure dependence for the heat capacity. So the temperature dependence is well represented by a polynomial. So it's quadratic, and then some species fit better to an inverse quadratic, so then there's a fourth term on there. And the integral that we're trying to evaluate now, this one is similar to what we did for enthalpy changes. The main difference for this entropy change is that we have the 1 over t in the integrand. So what we're going to do next then is we're going to look at that integral. So the integral of CPIG over RT dt from t0 to t is going to be the integral from t0 to t of a over t plus b plus ct plus d t to the minus third dt. We can integrate that term by term. I'm going to get a natural log t over t0 plus b delta t plus c over 2 delta t squared, and then minus 2 times d times delta t to the minus 2. That's pretty straightforward to evaluate, and so that's one way of accounting for temperature dependence. Now, one thing that we will talk about is mean heat capacities at this point. So in chapter 4, the text talks about a mean heat capacity for enthalpy, and I'll just review that real quickly. So if we go back to chapter 4, sensible heat effects, and I'll page down a little bit here where we get introduced to these heat capacity integrals. You can see that for the enthalpy change, there's the kind of the standard integral, and then equation 410 is interesting. It says even for a temperature dependent system, what you can do is define a mean heat capacity, and that's denoted as bracket CP with a subscript H. And the utility of a mean heat capacity is that rather than write the integral sign, what it looks like algebraically is similar to what you would have for the case where you were neglecting the temperature dependence of the heat capacity. So what do I mean by that? I'll say it again in a slightly different way. So our equation 26 for CPIG not equal to a function of temperature, which is always an approximation, you can write delta H for the ideal gas is equal to CPIG times delta T. Now, for the general case, for CPIG equal to a function of temperature, which is always going to be more accurate, your delta H IG, this is defined as your heat capacity integral. But if you divide that by delta T and multiply it by delta T, what we get is the following. T0 to T CP IG over R dt. There's the integral in the numerator. And then we just simply divide and multiply by delta T. And then this whole term right here becomes a quantity that's defined purely for algebraic convenience, CPIG, the subscript H, to remind us that this is for enthalpy calculations, times delta T. And if we look in the text, we get a nice compact definition for that quantity. So, and that is, of course, right here. So the average heat capacity for heat capacity integrals divided by R is just given by this algebraic expression. So it's equation 4.9. Now, likewise, for entropy integrals, we can do something very similar. So let's call this equation 28. And we go back up here. So this quantity, equation 25, I'll get that selected so I can copy it. And I will plop it down here. Uh-oh. And sometimes copy and paste just does not work in OneNote. Okay, there we go. All right, so there is my heat capacity integral again for entropy. So my delta S Ig over R is equal to this part. That's the integral. This integral is Cpig over R times dt over t from t0 to t. And then we just got to remember to incorporate the pressure effect of an entropy change. So that's, subtract the logarithm of the pressure ratio. All right, so if we had a heat capacity that was not temperature dependent, then what that would mean is that this whole thing would reduce to delta Sig over R equals Cpig over R times the natural logarithm of t over t naught minus the natural log of the pressure ratio. All right, so now we want to define the mean heat capacity such that we can write the same thing, except we're going to replace this part with the mean value. So for Cpig equal to a function of temperature, what we're going to have is delta Sig over R, and now that is going to be equal to this whole thing. That is the integral. And then we're going to divide it by natural log of t over t naught, and then multiply it by natural log of t over t naught. And we've still got the logarithm of the pressure ratio in there. And so now this whole thing is now what we define as our mean heat capacity, which is useful for entropy calculations. So the way that that is going to be annotated is Cpig, the subscript S. All right, so that's one algebraic form that is correct that you can use to calculate that mean entropy heat capacity quantity. We go to your equation sheet. There is a related form that introduces the parameter tau. Parameter tau is just a substitution for that temperature ratio. And 5.13 is in fact the equation that the text printed in earlier editions. In the current 8th edition, they've dropped the tau, which is fine. It doesn't change the result. So if you go to section 5.5, and we can come down to equations 511 through 513, we get the present formatting of that heat capacity mean value, which is given by this formula. Okay, so what we're going to look at next then is an Excel demo as to how do we actually calculate or make state change calculations for ideal gases. And once we get the formulas in new Excel, things will be a lot easier for us. All right, so for the next part of this video, what I'm going to do is show you how to make a spreadsheet like this that automates the calculations of both enthalpy and entropy changes for ideal gases. So what we're looking at here is I've set up a table, and I'm going to reproduce this from scratch for you all. I've got the first 4 columns. Those just store the coefficients that we pulled from Appendix C for the heat capacity correlations. And for this example, what we're going to be doing is we're going to be looking at methane. And there's going to be 2 cases. One is going to be pretty simple plug and chug. We want to know what is delta S for a state change starting at 433 Kelvin and 58.2 atmospheres, and we're going to be going colder and more compressed. So 298 Kelvin and 40 atmospheres. All right, and so to do that, what we're going to do is we're going to set up this section of the spreadsheet next. And so this is where we're going to put in the initial conditions. So the initial temperature, the initial pressure, the final temperature, and the final pressure. And then we're going to calculate various quantities. So the next section, the enthalpy section, there's 2 parts to that. The first part, we're going to evaluate the heat capacity integral directly. And so with respect to the text, that's the section 4 integral. If we divide the result by the temperature difference, we're going to get to the mean heat capacity integral. So column J has this equation, 4.8, embedded in it. Column K is evaluating this equation. Sorry, this one, for 9. And then column L is evaluating 4.10. The next section is the enthalpy section, or sorry, the entropy section. And that's going to cover the material that I just derived in the previous video. So those are the entropy integrals. So column M just does the integral directly. And so that's essentially this ICPS function that the text talks about. And then column N is implementing this equation for the average heat capacity. So the one that you multiply by the logarithm of T over T naught to get to the temperature contribution to a change in entropy. And then the final column is the resultant change in entropy for the process. So for the first process, the answer is going to be about minus 11.5 joules per mole Kelvin. All right. So then what we're going to do is open up a new book and see what I did to develop this. All right, so I'm actually just going to save this. And this is in my Section 2 lecture notes folder if you want to look at my work. So I'm going to save a new copy of this, and then I'm going to delete the formulas so I can talk you through how I put it together. All right, so first of all, I'm going to just copy those numbers because they're going to become useful in a minute here. All right, so I'm going to walk you through the setup here. So do you see these drop-down boxes that are in each column here? If you haven't used this feature in Excel before, it's really handy. So I'm going to make, it's just called a table. So I'm going to make a real quick table for you. I'm going to start with some column headers, X and Y, and some X values. So let's suppose I had an equation Y defined in terms of X, and I wanted to manipulate that in Excel. An easy way to do that is to drag the range where those data are going to live, and then in the Home tab, you're going to click Format as Table under Styles, and then you're going to pick your favorite formatting scheme. This dialog box appears, and it says where's the data. It's going to be where you have selected, and then you're going to leave the My Table Has Headers box checked. And so that's how that formatting came about. Now, you can do cool things like sort, so I can go from largest to smallest, or smallest to largest. But another nice thing that I can do is I can talk about values in the X column by name rather than by cell coordinates. So for example, if I want to say y is equal to x squared, rather than saying y is equal to b22 squared, I can say y is equal to x squared. All right, so I want to point a couple things out here. So the first is the square brackets means that you're going to be using table nomenclature rules. So to access a different part of a table, you're going to start with the square bracket. The @ symbol means you want to access a value from the current row, and then the text X after that is just simply the name of the column, and then at that point it's just hit enter and the formula is executed, and you'll note that the formula automatically populated down the rows of the table. Now you see the autocorrect thingy goes up there. You can undo that if you want, so either Control-Z, the undo arrow up here at the top, or you can use this drop down if you want different formulas for the different rows. But oftentimes that automatic filling behavior is convenient. All right, so that's how I set up this table up here. As I started with the column headers, played around with the formatting so everything looked nice. I selected this region, and then Home, Format as Table to get the nice drop-down boxes. To get to final results, I need the ideal gas constant. So I put that as a parameter up here at the top. And if I click on the actual number, if you're paying attention up here in the name box, you can see that I gave that number a special name. I called it R underscore. And that means whenever I use R underscore in a formula, so say down here, the autocomplete text shows me that that's something that Excel knows about, and if I hit enter, there it is, there's that value. All right, so why did I call it R underscore and not just R? The reason for that is that Excel has reservations on the character R and the character C because those are used as a different way of addressing cells. So you can't have just plain old R, plain old C is a cell name. Okay, so let's get started then with populating this with numbers. So the numbers came from Appendix C, and hold on, I want to grab those. Those are up here in my clipboard, and I'll paste those in. All right, so notice that I did not include the 10 to the minus 3 or the 10 to the minus 6 in those parameters. I actually did that intentionally just because it's one less thing for me to have to do if I copy new parameters into the spreadsheet. Now you might think that that's a bad idea, and you might be right, but that's how I'm going to do it. I'm going to account for the exponents I'm supposed to apply to those table data in the formulas themselves rather than actually entering the correct number. So of course, when I'm talking about is there's a 10 to the third multiplied by b before it's published, a 1 million applied to factor c before it's published, and if you have a d value, those have got to be scaled up by a factor of 100,000 as well. So back to the spreadsheet. So this next section of 4 cells, this is my user input region. So the first example I'm going to do, we're going from 433 Kelvin to 298 Kelvin. We're going from 58.2 atmospheres to 40 atmospheres. Now, one thing I'll note about these state change calculations for entropy is the pressure only appears as a ratio, so the units don't really matter. Okay, so for the heat capacity integral, I'm just going to be looking down here at equation 4.8 as I type. So that is going to be the A parameter, so bracket at A, and you can see that cell B5 highlighted in blue to show that I got it, times the natural logarithm of the temperature ratio. So I can either do that by typing it or by clicking on the cells. Either way is fine. So the first term, A times delta T. The second term, that is going to be B. Now remember to multiply by 10 to the minus 3, since I did not do that when I entered B, divided by 2 times T squared minus T0 squared. And then we're going to add C times 10 to the minus 6 times T cubed minus T0 cubed. So T cubed minus T0 cubed. And then finally, just for completeness, we can add the D term, even though it doesn't appear here. So for methane anyways. So multiply that by 100,000, so 10 to the 5th times, and then we're going to have T minus T0 in the numerator, and in the denominator we are going to have T times T0. And that should do it. So if I hit enter and all is good, I'll get a number. And I'm going to double check my work now. So A times, okay, right away I made a mistake. This is the H integral I'm doing, not the entropy integral. So A times delta T, and I think the rest of it hopefully is better. So A times T minus T0 plus B divided by 1,000 divided by 2, T squared minus T0 squared, C times 10 to the minus 6 times T cubed minus T0 cubed plus D times, yeah, I think that is about right. Good. And so the average heat capacity, I can either type in the formula or watch this. Since I'm already doing the full integral, and it's really not hard for me to do since I'm doing it in the spreadsheet, and it's just the heat capacity integral divided by delta T for the enthalpy. And I get a pretty reasonable value there for the average heat capacity. And so then the delta H, that is going to be the ideal gas constant times the average heat capacity times the temperature difference. And if I didn't want to use the average heat capacity, I could just use the heat capacity integral and not multiply by the temperature difference. So there it is. There's the result for enthalpy. For entropy, we'll start off with a full integral. So that's equation 511. So that is going to be A times the natural logarithm of the temperature ratio plus B, remember then 10 to the minus 3, plus C, remember the 10 to the minus 6, plus D, remember the factor of 100,000. All right, so I am right up to here in the equation. So now I need to divide by the product of T0 squared times T squared. And now I'm going to close off this portion of the expression, so that should match with this parenthesis up here, and it looks like it does. So now we're going to add in the average temperature term. So that is going to be T0 plus T divided by 2. And now we're going to close off the bracketed expression. It should match with B up here on the top. And now we multiply by T minus T0. T minus T0. Yikes, there it is though. So that should be the delta S, the temperature part of the delta S divided by the ideal gas constant. So ICPS R. Mean heat capacity then is going to be the actual heat capacity integral, and now this time we're going to divide by the logarithm of the temperature ratio. So the temperature ratio being T over T0 again. All right, and so I get a slightly different number for the mean heat capacity for entropy calculations versus what I get for enthalpy calculations. So that's about 4.7. All right, and so the final result then is just going to be R times the heat capacity integral. So I can get it that way. Or I can say it's R times the mean heat capacity times the logarithm of the temperature ratio. So natural log T over T0 once again. Okay, so that completes the construction of the first phase change. And so if we go back to what I'd marked up before, I'm getting the same numbers. All right, so second row, I'm just going to copy and paste that. So the next state change I want to do is I want to take, again, I want to take methane, and I want to start at 298 K, and I want to start at, let's see what I have written down here, 10 atmospheres, and I want to go to a final temperature of 298 K. Wait, hold on. I want to go to a final temperature that's unspecified. We'll get to that in a second here. A final pressure of 40 atmosphere. And so my final constraint is I want this compression to be adiabatic, which means that I want it to be reversible and adiabatic, which means that my change in entropy needs to be 0. And so what that looks like out of here. what that looks like is this cell in this row needs to say 0 when I've determined the right final temperature. So let's put in the pressure change. That's from 40 to 10. The temperature change is going to be from 298 to something. All right, I don't know what that something is just yet. So this is a good application of a numerical method. So let's show you how to use goal-seek here. So what I want to do is I want to adjust the temperature. So that's right here, the final temperature of a compression from 40 to 10 atmospheres starting at 298 Kelvin. I want to find the final temperature such that the final entropy change is 0. So I want the temperature change to cancel out the entropy change. So let's go up to data. And then up here, there's a bunch of stuff. Where I want you to go is what if analysis, and goal-seek lives right here. So goal-seek is a simple little tool. So what we want to do is I want to set this entropy value to 0, and I want to do that by changing the temperature. So I want to set cell O6 to value 0 by changing cell G6. So I hit go, and it's going to fiddle around until it gets to the right final value. Okay, and guess what? I goofed just a little bit here because I forgot something in the entropy change. So what did I forget? I forgot to account for the pressure term. So let's get that in there. So the pressure is going to be minus R times the logarithm of the pressure ratio. And wow, that's going to make a big difference. All right. So that populated down, so my formula has been corrected now. So let's do this again with goal-seek. So goal-seek, again, I'm going to set O6 to a value of 0, and I want to do that by changing the temperature. And there we go. And let's see, does that make sense? R times oh yeah, my result does make sense because I still have it in compression. What I wanted was an initial pressure of 10 atmospheres and a final pressure of 40 atmospheres. So let's do it one more time, and I should get the same value that I've got recorded here in my notes. So one more time, goal-seek, when I want to set cell O6 to a value of 0 by yet again changing the temperature. There we go. So you can see it fiddled around until it got to the final result, which is right around 403 Kelvin, and that is what I have recorded in my notes. You'll notice it's not super duper accurate. If you want more accuracy, then instead of goal-seek, we can use a more sophisticated tool called Solver, which is generally a better tool to use. We start with goal-seek because it's already available in all installations of Excel. Solver is a little bit different. Now you've got to go to the File menu and then Options, and then the default screen, it says Manage Excel Add-ins. You have to click Go, and then the Solver is actually an add-in tool that you have to manually select and enable. Now once you've enabled it, you shouldn't have to do it over and over again, but the first time you will need to do that. So now once the Solver tool is enabled, that also appears in the Data tab, and it's a new section in the Data tab under Analyze. So I click Solver, And there's a little bit more to it now, but it's still the same idea. It's just uses better numerical algorithms and gets you to better accuracy potentially, especially if you tweak it. So again, I'm going to set objective. The objective is this cell right here. I want it to have a value of 0, and I want you to get to that value of 0 by changing any number of cells that I select. So one advantage of solver versus GOLSI, because you can select more than one independent variable. So if you have a more complicated problem you want to solve, it can handle more than one independent variable. But again, I'm just going to select that final temperature. And then in the default implementation, I just click solve. And you'll notice that my entropy change is much, much closer to 0 now than it was before. All right. Numerically, that only changed the 10,000th digit. All right, so that is what I wanted to show you all. So I guess I will see you all on Monday, and have a great weekend. Oh, one last little thing. I just caught a mistake here in my enthalpy formula here. I'm missing the 1/3 factor for the C term. There we go. Now it's all correct. These two mean heat capacity values are different, but they should be fairly similar to each other in most cases.